Good morning to one and all. Today we are going to discuss about context-free grammar. In the previous classes, we have learned finite automata and regular expression. So regular expression and the regular languages. So regular languages are the languages which are accepted by the finite automata. In the Chomskyan hierarchy of languages, we have seen that apart from this RE, we have context-free language. So those languages are represented with the help of format called context-free grammar. That we'll see today. So the first we'll see the definition of context-free grammar. A CFG is a way of describing languages by recursive rules that are called production rules or substitution rules or simply called as productions. A CFG, that is context-free grammar, is denoted by four tuples J is equal to VTPS, where V and T are finite set of variables and terminals respectively. I mean, V represents set of variables, T represents set of terminals. We assume that V and T are disjoint set. There should not be any common element between this V and T. Then this P is a production rule, a finite set of production rule. Each production is of the form A tends to alpha, where this A is a variable. So we should have only one variable on the left hand side of the production, which is called head of the production. And right hand side of the production, we may have alpha. So alpha is a strings of symbols from variable union terminal the whole star. That is, we may have any number of variables and terminals at the right hand side of the production, whereas in the left hand side of the production we should have only one variable. So this is the format of the production rule. A tends to alpha. Finally, this S is a special variable called a start state or start symbol of the grammar. I'll repeat. The context-free grammar is a way of describing a language by the recursive rule, where we can represent the context-free grammar with the four tuples V, T, P, S, where V is set of variables, T is set of terminals, and P is set of production rules. Clear? Okay, we'll see one example. So here we have a context-free grammar with the four tuples that VTPS, where this V is going to have only one symbol, capital E. So we have to know that variables always represented with the capital letters. And the terminals are, other than the capital letters, what are the symbols available? Lowercase letters, special characters can be used for representing the terminals. Okay, so E. So here set of variable is E and set of terminals are plus, star, open parenthesis, close parenthesis, ID. Then set of production rule is capital P. So here you have a production rule like E tends to E plus E, E tends to E star E, E tends to open bracket E, close bracket, E tends to ID. Look at here at the right hand side of the production, you may have the combinations of variables and the terminals, whereas in the left hand side, you should have only one variable, that two variable. And here the start symbol is E. So here you have only one variable that is going to be the start symbol. So what does the grammar represent? This grammar represents the expression grammar. That is what it is represented with the capital letter E. Okay, so E tends to E plus E. What does it represent? Expression can be a expression with a plus symbol and followed by another expression, or expression maybe starting with the expression then followed by the star. Star is the multiplication. So mathematical expression, we're talking about the mathematical expressions. Okay, so E star E, or else you may have the parenthesis, open parenthesis, and the any expression. This expression may be with the plus operator, or the expression may be with the star operator, that is multiplication operator, then the closed parenthesis, or the expression may be simply any identifier. So this is a recursive procedure which represents the language, context-free language, which can represent the expression, any expression with a plus and star symbol. Or else we can write this production rule with the or operators like E tends to E plus E or E star E or open bracket E close bracket or ID. So we have to note something that always we have to use capital letters to represent variables. The variables are otherwise termed as non-terminals, and small letters or any special characters can be used to represent the terminals. So here also you can see capital E in order to represent the variable, and here you have IDs, lowercase and special characters like a plus, a star, open parenthesis, close parenthesis to represent terminal symbols. Okay, so next we'll see derivations and the languages. So a grammar is used to describe a language by generating each string of that language in the following manner. We can able to write down the start variable, then find the variable that is written down on right hand side that starts with that variable, and we can replace the written down variable with the right hand side of that rule. So we can able to replace the step 2 until no variable remains. The sequence of substitutions to obtain a string is called derivation. The sequence of steps which we do to obtain a string is called the derivation. Okay, so we can able to derive a string from the given grammar. Always you have to start with a variable, start variable. So start variable is a variable on the left hand side of the top rule unless specified otherwise. Always we have to consider the top rule left hand side variable as a start symbol. Okay, here you have only one variable, so no issues. You can take E as a start variable. Then what you have to do, find a variable that is written down on the right hand side that starts with that variable. Replace the written down variable with the right hand side of the rule, and we can repeat this until no more variable remain in the string. Okay, so this process, the sequence of substitutions to obtain a string is called derivation. Then we'll go to the formal definition of a derivation. So if A tends to beta, so what is A? A represents a variable. Beta represents always is alpha, beta, gamma are used to represent union of variables and terminals. Okay, so both variables may be combinations of terminals and variables. Is a production in a grammar G, and alpha, gamma are any two strings on variable union sigma. Here you can see the sigma. So sigma is nothing but the terminal. Okay, so you can read it as a variable and the terminal. Then we say alpha, the variable A, gamma directly derives alpha, beta, gamma in G. You had a production rule that A tends to beta, meaning you can be able to replace the capital A with a beta. So that what you can able to array? You can able to array alpha, beta, gamma. Since you have substituted A as beta, beta is any strings of variables and terminals. Okay, so this process is called derivation. This is the formal definition of derivation. So if there exists a production rule which is of the form A tends to beta, okay, then you are having some strings like alpha and gamma. Then this alpha, A, gamma can be written like alpha, beta, gamma, since you can replace this A by beta. Okay, so this process is called derivation. Clear? Then formal definition of the language. Then we'll see the definition of language. See, if G is equal to VTPS, we know we can represent grammar with a 4-tuple representation: variables, terminals, production rules, and the start symbol is a CFG. There's a context-free grammar. The language of G denoted by L of G. Okay, so language of this grammar can be represented as L of G is set of terminal string. So language, we know what is language. Language is set of strings, isn't it? So set of terminal strings. So terminals, why you should use terminal string? Always it should have only the alphabet. It should not have the variables. Okay. So set of terminal strings that have the derivation from the start symbol, that has the derivations from the, we have seen the what is derivation, isn't it? So when you can able to derive some set of string from the start symbol, then this is called then that set of strings are called the languages. Okay. So how can we write in formal? L of G, that is language derived from the grammar. L of G is equal to set of W. So W, when we use W, W is represent the string. Okay. Set of strings in T star. So what is the meaning of T star? It is uh, any number of terminals. Okay, any number of terminals. So T star may include epsilon also, such that it should start from S. So S derives W over the multiple set with the help of the G. So S derive star G you have. What is the meaning? Using the grammar G, by taking the multiple step, star always 0 or more. Okay, by taking 0 or more steps, we can able to arrive at the W. W is nothing but set of strings. Okay, if the language L is the language of some context-free grammar, then L is said to be context-free language. If the language is derived from the context-free grammar, then the language is said to be context-free grammar. Okay, previously we have seen regular language, isn't it? Regular languages are accepted by finite automata and it can be expressed with a simple expression called regular expression. So here today we have learned a new language, context-free language, which are the strings which are derived from the context-free grammar. What is context-free grammar? Context-free grammar can be represented with the four tuples V, T, P, S. It is a recursive procedure to represent any language. Okay. So we will see one example to that. So L of G is equal to W such that W is in L T star and S derives W. What does it mean? Okay, what is the meaning of this? So W is a string such that a string consists solely of terminals. Most important. Okay, W is in T star and string can be derived from S. So both conditions should be satisfied. You have and here, isn't it? So always the W should contain only the terminal string and it should be derived from the start symbol. Okay. Construct the language L of G for a given C of G. G is equal to V, T, P, S, where V is equal to S, only the start symbol. T is equal to A, B. There are two terminal symbols A and B. And production rules, S tends to ASB, S tends to AB. So what is the language derived from this grammar given? It's very simple that S, we have to start with the start symbol. Okay, so S is the start symbol. So for this S, you have two options. Suppose you are starting with this ASB, then you can keep on substitute S by ASB, so that at last what you can able to conclude, this is a grammar which can able to derive the language A power n, B power n such that n is greater or equal to 1. So what is the meaning? Any n number of A's followed by n number of B's. So this is the grammar with the four tuples V, T, P, S. It can able to generate the language L of G, which is equal to A power n, B power n such that n is greater or equal to 1. Okay, we'll see another example. Let G is equal to SC, AB, PS. So the first set represent the variable, second set represent the terminal and the production rules and the start symbol. And we have given with the production rule like S tends to A capital C A. So capital letters represent the variable, small lowercase letters represent the terminal. So that's what we can see. V is equal to S comma C, isn't it? So S tends to A C A, C tends to A C A or B. Now you are asked to find out the language generated from this grammar. Okay. From this grammar, we get the string such that. So what we have to do, you have to substitute. You have to start with the A's and you can substitute. When you start with this A's, you can substitute this capital C either by ACA or B. Suppose you are substituting the C by A. Sorry, the C by B, because the C can be replaced either with ACA or B. So suppose you are replacing it by B. So then what will we be getting? We'll be getting ABA. Okay, and again you suppose you are substituting it with A, C, A, and again C is replaced with B. Then what is the next string which you can able to get? A, B, A. Okay. So triple A, B, A. So how can you define it in general? A power n, B, A power n. So this is the grammar. S tends to A, C, A, C tends to A, C, A or B, can able to derive the language. So what is the language it can able to derive? A power n, B, A power n such that n is greater or equal to 1. Okay. Similarly, we'll see another problem. Find L of G for G. S tends to A, S, B, B, S. S tends to A, B, B or epsilon. Okay. There are 3 production rules given. And we didn't explicitly given with the variables terminus and the start symbol, but you can able to identify the variables terminus and the start symbol. Always the first symbol whose head is called start symbol. So here you know you have only one variable capital S, that is going to be the start symbol. Okay, and the capital letters represent the variable. So you have only one capital letter S. So S is a variable. And terminal. So other than the capital letter, what are the symbols you have? A, B. You should not include this null string in the T. Okay, it's a null string. You should not take it as a alphabet. Okay, so small a, small b are T. Okay, so next what you have to supposed to do, you have to find out the string which are derived from the S. So we can able to see the primitive string is epsilon, because you have a straight production rule that S derives epsilon. So epsilon can be derived, and also S tends to ABB. You can able to derive ABB. Okay, then you can go to this recursive procedure where you can able to understand that you can able to get AA, BB, BB, triple A, BB, BB, BB. So there are six Bs. So what is the general format? Very simple. Can anyone tell? Yes, A power n, B power 2n. So this is the language derived from this grammar given. Okay, next. Construct context-free grammar for the regular expression 0 plus 1 the whole star. Okay. What is the meaning of 0 plus 1 the whole star? Any strings of zeros and ones. So now you're asked to write a context-free grammar to generate this expression 0 plus 1 the whole star, to generate this language, regular language. Okay. We know that regular language is subset of context-free language. So you can represent regular language with the context-free grammar also. Okay. So for that, you have to use a start symbol. For example, S tends to 0s or 1s or epsilon. Okay, where B is equal to S and T is equal to 0, 1. So this is the grammar. Okay, it can able to generate 0 plus 1 the whole star. 0 plus 1 the whole star is nothing but any binary string including epsilon. Okay, next we'll see the next problem. Construct the context-free grammar for the language having any of A's over the set sigma is equal to A. So any number of A's, how can you represent any number of A's? It is A star. Okay. So A star should be generated by the grammar which you are going to write. So very simple. S tends to SA or epsilon. So this is the product. These are all the production rule which can able to produce any number of A's. So including epsilon. Next, construct a grammar for the language containing two A's over the set sigma is equal to A comma B. Okay, so sigma is A comma B. The terminal is A comma B, but it should the language, the grammar which you are going to write should give the language that should contain two A's. Okay, so two A's. So A, and this A can be any strings of A's and B's. That's what S tends to A, small a, small a, A. Okay. So two A's, at least two A's it should have. Okay. And any strings of A's and B's at the beginning, middle and the end you may have. Okay. That's what this capital A is, any strings of A's and B's. So any strings of A's and B's can be represented with small a capital A, small b capital A and the epsilon. Okay. So this is a grammar which can able to generate a language containing two A's over the set sigma is equal to A comma B. And the next problem. Construct a CFG for the language L, which has all the strings which are all palindrome over the set sigma is equal to A comma B. That is palindrome W power R. So here, since it is given as W power R, what you can able to understand? So palindrome, very simple, palindrome. Okay, so G is equal to VTPS, where V is S, P is equal to S tends to ASA, S tends to BSB, S tends to A, S tends to B. So this is the grammar which can able to produce palindromes of odd length. Similarly, you can also write a grammar which can able to produce palindrome of even length and both. Next, construct a grammar generating L is equal to WCWT. Okay, transpose of this W. Okay, which is nothing but the reverse of W, where W is equal to A plus B the whole star. What is the meaning of A plus B the whole star? Any strings of A's and B's. Okay, first you have to identify the set of strings. So C. So whenever this W becomes epsilon, W power T is also epsilon. So that you will be getting resultant with only C. Suppose you have W as A, then ACA. If you have W as B, then BCB. Suppose you have W as AB, then ABC BA. Okay, transpose or reverse. Okay, so how can we generate a grammar for that? The previous thing you can take as such, but in the middle you should have a C. So that what you can do, S tends to A as A, S tends to B as B, and this middle can also be represented with a small c. Okay, but we have added one more terminal C, so that T becomes A comma B comma C. Apart from that, it is similar to the previous grammar, the palindrome grammar, but here you should have a copy character C here. Next, construct a context-free grammar which consists of all the strings having at least one occurrence of 000. That is 3 consecutive zeros. Okay, at least one occurrence. More than that also you may have, isn't it? But in between you should have 3 zeros, consecutive zeros. So definitely the general format will be, the recursive procedure will be S tends to S000 S, and S tends to any strings of zeros and ones. So any strings of zeros and ones can be represented as 0, 1, S. Next, construct a context-free grammar for the language containing at least one occurrence of WA over the set A comma B. So WA over the set A comma B. So in between you may have WA, and before and after you may have capital A. This capital A may be any strings of A's and B's. Very simple. S tends to capital A, small a, and this capital A is what? Any strings of A's and B's. How can we represent any strings of A's and B's? Capital A tends to small a capital A, small b capital A, or epsilon. Or you can also write capital A small a, or capital A small b, or epsilon. That is also correct. Okay, are you clear about what is grammar and what is language, context-free language, and what is context-free grammar? Yes. Next we'll see derivation tree. Okay. So derivation tree is nothing but a graphical representation for the derivation of the given production rule for a grammar, context-free grammar. The derivation tree is also called a sparse tree. It is usable to display the derivation as a tree. So here we can able to represent the derivation in the form of a tree, graphical representation. Okay, it is otherwise called a sparse tree. Next we'll see the properties of any derivation tree. Let G is equal to VTPS. So just take a grammar with the 4 tuples: variables, terminals, productions, and start symbol. Be a context-free grammar. A tree is a derivation tree for G if it should have these properties. Okay. Number 1, every node, that is every vertex of the graph, has a label which is of the symbol variable, union, terminal, union, epsilon. Okay. Every node of the graph which we are going to draw should have a label, and the label can be a variable or a terminal or epsilon. Okay, this is the first property. Second property, the label of the root is S. So always the root node should be labeled with the start symbol S. Okay, the label of the root is always S. So S is nothing but the start symbol. Third point, if a vertex is the interior, okay, suppose you are going to talk about the interior vertices, okay, then it has a label A, then A must be in variable. So all the interior nodes of the parse tree or the derivation tree which we are going to draw should have the label called variable. It should not be the terminal. So interior node. So we have seen that start node is a root is a root must be labeled as yes, that is the start variable. Similarly, all the interior nodes are to be labeled with variable. Clear? Okay. Fourth point. If n has the label A and the vertices n1 and so on nk are sons of vertex, okay, in order from the left with the labels x1, x2, xk respectively, then there is a production A tends to x1, x2 and so on xk. Okay, so what you can able to say, suppose if you are having an interior node with a variable, then whose children, okay, suppose it is marked as x1, x2 and so on xk, then there should be a production rule in the grammar that A tends to x1, x2 and so on xk. In fifth property, if the vertex n has a label epsilon, okay, so any vertex and we can able to see epsilon is a label, then n is a leaf node, okay, then that vertex must be a leaf. And one more important rule, that it should be only one son of its father. It should be only one son of its father. Clear? Okay, so we have to note something, that root node always starting non-terminal, okay, interior node or non-terminals, otherwise called variables, and leaf nodes are terminals, or sometimes you may have epsilon. If you are having epsilon, that should be the only one son. Clear? And always we have to read the tree from left to right. Let's see an example. Consider a grammar G with the production rules. S tends to small a, capital A, yes, or small a. So always the lowercase letters represent the terminals, uppercase letter represent the variables. So here you have two variables, S and A, and two terminals, small a, small b. And there are three production rules. Okay. And derivation tree for the string A, B, A, A. So how can we derive this A, B, A, A? Always you have to start with the S. Okay. And S has two production rules. AS, AAS or A. We know that we have to choose this small a, capital A, S in order to produce or in order to generate or in order to derive the string A, B, A, A. So when we take this small a, capital A, S. Okay. So this yes can have its children like capital A, small a, capital A, yes. And again you can replace this capital A with BA and this yes with A. So this is the parse tree for this grammar to generate the to derive the string A, B, A, A. So look at here. So the root node is yes. Okay, always the start symbol should be given in the root node. Okay, the root should be labeled with the start symbol. So what are the interior nodes we have? A and S, capital A and S. So these are all variables. And what are the leaf node? This A, this B, this A, this A. So leaf nodes are nothing but the terminals. So this is the example for derivation tree. Okay, next. Consider G, the grammar, whose productions are S tends to small a, capital A, yes, or A. And A tends to capital S, B, capital A, or yes, or B. And show that yes derives over a multiple step. What it can able to derive? AA, double B, double A. And construct a derivation tree whose yield is this string AA, double B, double A. Okay, so we are supposed to derive this AA, BB, AA, and we have to construct a tree for that. Okay, how can you do? always you have to start with the start symbol. So start symbol yes. So we can choose yes with the, and we can replace this yes by yes. Sorry, yes. Okay. Next, you can choose this A to replace by its any of the production rows. So here you can replace this A by SBA. Okay. Again, you have to replace this S by A, and then you can replace this A by BA. At last, you can replace this S by A, so that when you collect the leaf nodes from left to right, you can able to get AA, BB, AA. Okay, so this is about the derivation and the derivation tree. So each and every derivation can be represented with a graphical representation called derivation tree or parse tree. Okay, this is another example. Construct the derivation tree for the string double A, double B, double A, double B for the given grammar. Okay. So always you have to start with S. So S has the production AB. So you can replace S by AB. Again, this B has to be replaced by its any of the body. So this B can be, suppose it can be replaced with ABB. Okay. Then again you have to choose any one of the non-terminal and you have to replace with by its body. Okay. Suppose you are replacing this B with BS. Okay, then you can replace this yes with VA. Again you can replace this A with ES. Again you can replace this S with AB. Again you can replace this B with small b. Again the last B with a small b. So what we have arrived at? We have arrived at the string AABB AABB. So this is a string we are supposed to derive from this yes start symbol. Now we can draw a corresponding parse tree for this derivation. So S is derived as AB. Okay, so yes with the two children AB. So we know this A is terminal; it cannot be further derived. Okay, expanded. But we can take this B. So B is replaced with ABB. Again, you can take this B and you can replace with BS. And again, this S can be taken and it can be replaced with BA. Again, this A can be taken and it is replaced with AS. Again, this S is replaced with A capital B. Again, this B is replaced with B and the last B is replaced with B. Next, how can you get the yield? Yield is obtained by reading the leaf node from left to right. So when we read the leaf nodes from left to right, we can get A, B, B, A, B, B. Clear? Okay. Next, subtree. So previously we have seen the definition of tree and the properties of tree. Now we are going to see about subtree. So what is subtree? So a subtree of derivation tree T is a tree satisfying the following constraints. So subtree should satisfy these following constraints or the conditions. Number one, whose root is some vertex V of T. Okay. Then whose vertices are the descendant of V together with their weight labels. Whose edges are those connecting the descendant of V. That is, a subtree looks like a derivation tree except that a label of the root may not be the start symbol of the grammar. Okay. See, when we consider a grammar and a derivation tree to derive a string A, B, B, A, then this portion, okay, this portion. So here it is clearly written A, S, B, A, B, B. So this is called a subtree. It's a part of a tree. Okay, clear? Next. See, next we are going to see the equivalence of derivation and the derivation tree. So there exists a relationship between the derivation and derivation tree. For that we have a theorem. Okay, so I'll read the statement of the theorem. Let a grammar G, which is equal to B, T, P, S. Okay, it's a contextual grammar. Then prove that yes, multiple derives some alpha. If and only if there is a derivation in, tree in the grammar G with yield alpha. Okay, so starting S is a start symbol of the variable and alpha is any string. Okay, if so, we can able to construct a derivation tree, okay, from the grammar G, which can able to yield. So yield is nothing but when we collect the leaf node from left to right is called yield, okay, which can able to produce alpha. So how can we prove this? So here what we have to prove is that for any A in V, so A derives alpha if and only if there is a tree with alpha as the yield. Okay. So first we'll see the basis step. Assume that there is only one interior node A. Okay, only one interior node A. The derivation tree yields x1, x2 and so on, xn. In that case, x1, x2, xn must be terminal. Okay, suppose if you have only one interior node and it should have uh, uh, some uh, um, some children which are labeled as x1, x2 and x1, and these should be terminal. Okay, so this x1, x2, xn can be written like alpha 1, alpha 2 and so on, alpha 1. In general we can write it like alpha. Okay, so it is proved in the basic case. Okay, then we are going to the inductive step. We assume that the derivation will enable us to draw the derivation with k minus 1 interior nodes. Here we have to prove that it is possible to draw a derivation tree for k interior nodes, which gives the string alpha. So consider the sums of the root A as x1, x2 and so on, xn. So then surely we have a production rule A tends to x1, x2 and so on, xn, isn't it? Okay, so case 1. Let us assume vertex I is a leaf. So what you can do? You can replace this xi by alpha I straight away. And if it is not a leaf, what you can do? You suppose you will be replacing it with any other way, non-terminal, and again that non-terminal may have a production, so that you can substitute that production as a children, isn't it? Anyway, this A can able to yield some alpha. So that is A, x1, x2, here it is a terminal, and this can also have, you can expand. Suppose this x2 has a subtree that can able to produce some alpha. Then this suppose this x3 is a terminal and xn minus 1 is a variable, then it can able to generate a subtree and it may yield something. Okay, so every derivation has its own derivation tree. If you are having a derivation tree, definitely you'll be having a derivation. So that from this you can able to conclude that. Okay, next. So when we talk about the language, definitely we'll be having an ambiguity. Similarly, some of the grammar may be ambiguous grammar. Okay, so if in order to learn about this ambiguity of the grammar, first we have to know two set of derivations, leftmost derivation and the rightmost derivation. Okay, first we'll see about the leftmost derivation. The leftmost derivation is a derivation in which leftmost non-terminal is replaced first from the sentential form. Next, rightmost derivation. The rightmost derivation is a derivation in which rightmost non-terminal is replaced first from the sentential form. Just consider a grammar S tends to X, Y, Z and X tends to A, Y tends to B and Z tends to C. Then what is called leftmost derivation? We have to take the leftmost non-terminal. So we know that S can be replaced with X, Y, Z. Okay, so S derives. So now we are going to use leftmost derivation so that you can use LM. Okay, so X, Y, Z. Next, since it is a leftmost, what you have to take? You have to take the leftmost non-terminal to replace by its body of the production. Okay, so this we have to take the X, and you know X can be replaced with A. And out of these two, Y and Z, Y becomes a left. So this Y is replaced with B. And next you have left with only one non-terminal, that is Z. You can replace it by C. Next we'll see rightmost derivation. So yes, the so here we have to take the rightmost non-terminal. So Z is the rightmost non-terminal. It can be replaced by C. The next step, Y becomes the rightmost non-terminal. So that can be replaced with D. And next, x is a only non-terminal, we can replace it by a. Okay, so now we are clear with leftmost derivation and the rightmost derivation. When you choose a leftmost non-terminal to replace by any of its body, then it is called as leftmost derivation. When you choose a rightmost non-terminal, always when we choose rightmost non-terminal to replace by its any of its production, then the derivation is called rightmost derivation. Okay, then we'll go to this ambiguity of the grammar, because the ambiguity of the grammar is defined with the help of these two terms, leftmost derivation and rightmost derivation. That's what we have seen, the definition of leftmost derivation and rightmost derivation earlier to this ambiguity of the grammar. Okay, what is ambiguity of the grammar? The grammar can be derived in either leftmost or rightmost, isn't it? If there exists more than one derivation tree or the past tree, okay, that means if you can able to derive a string with a different manner, or else if you can able to construct more than one pass tree for a same string w for the given grammar, then the grammar is said to be having ambiguity. We'll see one example for that. Check whether the given grammar is ambiguous or not. So you are given with expression grammar. E tends to E plus E, E tends to E star E, E tends to ID. Okay, so leftmost derivation and rightmost derivation. Suppose you want to derive ID star ID plus ID. Okay, yes, you are doing this with, you are taking E tends to E plus E initially. Then this E is replaced with E star E. Again, this E is replaced with ID, and another E is replaced with ID, another E is replaced with ID. At last, the string which we have derived is ID star ID plus ID. Okay. Next, we'll see the rightmost derivation. So here we have taken E star E initially. Then the rightmost non-terminal capital E is replaced with E plus E. Again, this rightmost non-terminal E is replaced with ID. Again, this rightmost E is replaced with ID. Again, we have left with only one E which is replaced with ID. Okay, we have derived the same string ID star ID plus ID. But when we look at the tree, okay, using LMD, you have E tends E plus E star E, ID, ID, ID. But here E star E. So here you have plus, here you have star. So two different parts you have arrived to generate a same string ID star ID plus ID, isn't it? So that what you can able to conclude, this grammar is ambiguous grammar. I mean, whenever you can able to construct more than one pass tree to derive any string W from given grammar, then the grammar is said to be having ambiguity. Okay. Next, you are given with the grammar and also a string. You are asked to find out its leftmost derivation and also to draw the derivation tree. Okay. So here you have a production rule and you are given with the W 0 0 1 1 0 1 0 1. You're asked to derive this string using leftmost derivation. So you know what is leftmost derivation. You have to always choose the leftmost non-terminal to replace. So we are starting with S tends to 0B. Here you have only one non-terminal. No issues. You can replace that with any of its production. Suppose you are replacing this B with 0B again. Next, in this step you have two B's. One is at left, another is at right. Okay, always you have to choose leftmost non-terminal to replace for leftmost derivation. So choose this B, and you can replace it 1s. Okay, again you have two non-terminals S and B. Again you have to choose the leftmost non-terminal S. Okay, and this S can be replaced with 1A. Again you have two non-terminals A and S. Again you have to choose the leftmost. So A is the leftmost, so that you can replace this A by 0s. Ahead you have two options S and B. This S can be replaced with 1A. Again you have two options A and B, and this A can be replaced with 0. At last you have only one non-terminal B that can be replaced with 1. So at last we have got the string 0 0 1 1 0 1 0 1. It is the string to be derived. Okay, the corresponding derivation key is here. So S is replaced with 0B. This B is replaced with 0BB. And the leftmost B is replaced with 1S. And this S becomes the leftmost and it can be replaced with 1A. And this A can be replaced with 0S. And S can be replaced with 1A. And A can be replaced with 0. Clear? At last, we can replace this B as 1. So, yields of the tree. Always you have to collect the leaf node from left to right. So, when you collect the leaf node from left to right, we can be able to read that 0, 0, 1, 1, 0, 1, 0, 1. So, this is the string to be obtained. Clear? Okay. If G is a grammar, S tends to SBS or A. Show that G is ambiguous. Okay, you are given with the grammar and we are supposed to show the given grammar is ambiguous grammar. How can we do? We have to derive any string from this SBS, the given grammar, and it should have two different parts. Okay, so here by taking this AB, ABA, we can able to derive this string AB, ABA with a two different manner. So first SBS and then this S can be replaced with SBS, but here it is replaced with A. So if we can able, so you can see that this tree is a mirror image of this tree, isn't it? So both are looking different. It's a mirror image. So since we have drawn two different parts tree, what you can conclude? That G is ambiguous. Clear? Next, consider a grammar G. Show that this grammar is ambiguous, and also we required to derive a string given. Okay, so for this string A, B, B, C, C, D, D, we can derive using leftmost derivation, and this is a corresponding parse tree. And also the same string can be derived with another leftmost derivation. Okay, so yeah, the condition is you should have more than two parse tree. Okay, so here same leftmost derivation used, but we have got two different parse tree. So that what you can conclude, the given grammar is ambiguous grammar. Clear? Next we are going to see simplification of context-free grammar. It's most important. Whenever you are given with the context-free grammar, we have to simplify them before converting to a normal form. Okay. For the simplification of CFG, we have to go through three different steps. The first step is elimination of useless symbol. When you call the symbol as useless symbol, the following approach are used to identify the symbol has to be able to do the following useful. See, first we say X is generating if X can able to derive a W for some terminal string W. We say X is reachable if there is a derivation S tends to alpha X beta for some alpha and beta. So what you can able to understand from here, when you say the symbol as useful only when it is generating and it is reachable. Generating in the sense it should produce any terminal string. Reachable in the sense this X should involve from the S. It should involve in derivation of any string from the starting symbol S. So here you are given with a production rule. It consists of some set of variables and terminals. So what are the variables you have? S, A, B, X, and also D you have a non-terminal D. Okay, and A and B are two terminals, and also you have D, isn't it? So you have some set of variables and terminals. Now you are asked to identify and eliminate the useless symbols. Clear? See, what is the first step? You have to find out generating symbol. Okay, so A is generating. Look at here, A tends to small a. So when you say a symbol as generating symbol, only when it can able to produce a terminal string. So A derives small a. Okay, and X is also generating. X tends to AD. Okay, X is also generating. Since the X is is a useful symbol, A is also S is also generating, because look at here. You have Bx. So this X can be replaced with AD. So S can able to derive a terminal string that BAD. Okay. So what is the conclusion we have got? This A is straight away generating, X is generating, S is generating. But This B is not generating. So what you have to do? You have to eliminate B. So you have to remove wherever you have B. So you can eliminate this production and this production and the complete B production, and then these two things. Wherever you have B, you can eliminate. Okay. So that you can rewrite the grammar as S tends to BX, A tends to BSX, and X tends to AD. Next, what you have to do? You have to find out the not reachable symbol. Okay. So X is reachable, but not S, but not A. A is not reachable from S. So that what you can do? You can eliminate A. At last, you can have the usual production rules as S tends to BX and X tends to AD. And the next step is to eliminate epsilon production. Okay, that is to find out the nullable symbols. See here you have P tends to epsilon. This is called epsilon production. So we'll be seeing the steps. First we have to identify the nullable symbols. Okay, B, C are directly nullable because B generates epsilon and C generates epsilon. So you can able to know that B and C are directly nullable. Next, A is also nullable because we have A tends to BC. So when you substitute BS epsilon, CS epsilon, what you can able to get? AS epsilon. So A is also epsilon. Finally, since you have S tends to ABC, what you can able to conclude? This S is also nullable. So you have to eliminate the nullable variables. So how can you eliminate a nullable variable? Wherever you have nullable variables, you have to substitute epsilon and you have to generate a new production. Okay. So when we substitute the C as epsilon, you will be getting AB. A as epsilon, you will be getting BC. B as epsilon, you will be getting AC. And BC as epsilon, you will be getting A. And AC epsilon, you will be getting B. And AB epsilon, you will be getting C. Okay, wherever you have nullable variable, you have to substitute epsilon and you have to collect all the productions. Similarly, when you take this A tends to BC, so when you substitute BS epsilon, you will be getting C, CS epsilon, you will be getting B, and at last you may get A. Okay. So similarly, after substituting nullable variables as well, epsilon, we can able to arrive at these things. Okay. So here there is no epsilon production. And the third step is to eliminate the unit production. A unit production is a production of the form A tends to B, where both A and B are variables. Okay. See for example, E tends to T or E plus T. T tends to F or T star F. F tends to I or epsilon open parenthesis E close parenthesis. I tends to AB, IA, IB, I0, I1. So here what are the unit productions you have? E tends to T is a unit production. T tends to F is a unit production. F tends to ID is the F tends to I is the unit production. So we have to eliminate. So how can we eliminate? We know that I is AB, IA, IB, I0, II, I1. So this can be used here. So this F can be written like F tends to the earlier production open parenthesis E close parenthesis. Instead of this I, what you can do? You can replace it with its body, that is A, B, IA, IB, I0, I1. So now you have removed unit production from F. Now you can substitute this F and T. Okay, since you have F and T. Okay, instead of this F, what you can do? You can substitute this. Okay, so here these are all F and T tends to T star F. Already we have, instead of this F, we have substituted the body of the F. Similarly, in E tends to E plus T, T. Instead of T, you can substitute the body of the T as T star F, open parenthesis E close parenthesis, A, B, IA, IB, I0, I1. So these are the three steps you have to do in order to simplify the grammar. Okay. So some care must be taken when we go for the simplification of grammar. This is the safe order. First, you have to eliminate the epsilon production. With the resultant grammar, you have to eliminate the unit production. With the resultant grammar, you have to eliminate the useless symbol. So this is the safe order. We'll see one example for that. Begin with the grammar. This is a given grammar. First, what you are supposed to do, you have to eliminate the epsilon production, then the unit production, then the useless symbol. Okay. So to eliminate the epsilon production, so from the given grammar, you can able to see D is directly nullable. B is also nullable since you have B tends to D. And S is also nullable since you have S tends to BAB. So we can eliminate nullable variables from the grammar by substituting the nullable variables as epsilon, so that you can result with this set of production rules. That is, S tends to ABC, BAB, AC, AB, BA, A. A tends to AA, BAC, AAA, AC, B tends to BBB, A, D, BB, C tends to CA or CA. Okay, next what we are supposed to do, we have to eliminate the unit production. So from the resulting grammar, B tends to D is the unit production. So wherever we have B tends to D, we have to substitute the body of the D. Okay, but we don't have any body of the D. So simply we can eliminate this B tends to D, so that you can rewrite the grammar like this. Then we have to go with the useless symbol. Okay, so we have to identify the useless symbol. So in order to find the useless symbol, first we have to identify the generating symbol, non-generating symbol, and to eliminate. So S is generating, B is generating, A is generating, since we have the S, B, A, isn't it? So C is not generating, so we can eliminate C. So after eliminating, this grammar production is looking like this. Next, what you are supposed to do, you have to identify the not reachable symbols. Okay, S tends to BAB, AAB, AA. So here B is becomes reachable, whereas A is not reachable. So after eliminating A, at last you can able to get this grammar S tends to. See, initially we are given with so much of production rules. At last, after simplifying it, you are resultant with very few production rules, isn't it? So this is called simplification of grammar. Okay, we'll see another example. Simplify the grammar. S tends to 0, A0, 1, B1, BB, A tends to C, B tends to S or A, C tends to S or E. Okay. So here we can able to see, first step is to eliminate the epsilon production. So C is nullable because directly we are given with C tends to epsilon. So indirectly A is nullable, B is nullable, and S is also nullable. So you have to eliminate the nullable variables by substituting nullable variables as epsilon. So you will be getting these set of production rules. Next, what you have to do, you have to eliminate the unit production. So these are all the unit productions you have. Okay, so you can substitute all those body and you can eliminate. At last, you have to eliminate the useless level. So all are generating, but C is not reachable from A. So at last you can eliminate the C production. So this is the thing you can get at last. And one more example. Simplify the grammar. S tends to AAA, A tends to AA or B tends to epsilon. So always the first step to eliminate the epsilon production. So after eliminating the epsilon production, B tends to epsilon, you will be getting these. Then you have to eliminate the unit production. These are the unit production you have got, that S tends to A tends to B, and S tends to B. Okay, so you have to substitute the body of the unit productions. So at last, there is no useless symbol. Clear? So this is how you can able to simplify the given grammars. So today we have seen context-free grammar and context-free language derivations, and there are two types of derivations: leftmost derivations, rightmost derivation, and then ambiguous grammar. Okay, then we have seen the relationship between the derivation and the derivation tree. Then we have seen how to simplify the given context-free grammar. Any doubts? Okay. Thank you, students. With this, I'll complete today's session. The next class will learn about push-down automata, which is nothing but the context-free languages are accepted by the automata called push-down automata. So in the next session, we'll discuss about push-down automata. Thank you.